Imagine looking up at the night sky tonight.
Right?
For the most part, it's a really comforting view. It's the exact same canvas humanity has projected its myths onto for thousands of
The
years.
constellations are steady.
Exactly. The planets, Mars, Jupiter, Saturn, they move in these perfectly predictable clockwork paths that we can map out for centuries in advance.
It feels permanent. It feels safe.
It does.
Yeah.
But I want you to strip away that feeling of safety for a minute.
Sure.
I want you to imagine that something fundamental changes. And I don't mean a star exploding millions of light years away, which is, just a pretty light show for us.
Right, a supernova.
Yeah, I mean something right here, on our doorstep.
And we should clarify right out of the gate, this isn't the standard Hollywood asteroid scenario.
No Bruce Willis today.
Definitely no Bruce Willis.
Or not.
We aren't talking about spotting a shiny rock and sending a drilling team. We are talking about an astronomical discovery that defies our immediate intuitive understanding of the solar system.
So set the scene for us.
Okay, astronomers detect a massive object entering the outer solar system. But here is the kicker. It reflects no sunlight.
None at all.
Zero. And it emits no radiation of its own. It is, for all intents and purposes, a ghost in the void.
See, that is the part that chills me. Because in every disaster movie, there's a distinct visual, right? A glowing comet tail, a tumbling gray rock.
Such a physical threat you can point a telescope at.
Exactly. But this object is chemically dark. I was reading the source material, and it mentions it might be covered in complex dark hydrocarbons, or maybe it's just so incredibly far from a star that there is absolutely no ambient light to reflect.
It is effectively invisible until it is dangerously close. We rely almost entirely on light to map the universe.
We look for stars burning, or we look for the reflection of that starlight off planetary bodies.
Right, so an object that absorbs light or simply doesn't have a nearby source to reflect is a phantom. We might detect it only by what it blocks.
Like an occultation?
Yes, an occultation, where it briefly snuffs out the light of a background star. Or, more likely, we'd detect it by its gravitational influence on other bodies in the outer solar system. We'd see things moving incorrectly.
Like the math suddenly stops working for objects in the Kuiper belt.
Exactly. And this phantom isn't just drifting lazily, it's moving with terrifying purpose. We aren't talking about the leisurely, circular orbit of a planet like Neptune.
It's not bound to our sun.
It is unbound to any star. It's on a hyperbolic trajectory.
Which in orbital mechanics just means
It means it's a one-way trip. It is cutting through the darkness like a bullet, not circling the drain.
and the speed of that bullet is hard to wrap your head around.
That velocity is key to understanding the scale of the threat here. When we look at the interstellar objects we have actually detected, like Oumuamua, which passed through our system a few years ago.
Right, the cigar-shaped one.
That's the one. It was traveling at roughly 29.3 kilometers per second relative to our sun.
Kilometers per second. Let that sink in.
Now compare that to a typical meteorite or asteroid that might hit the moon, which travels at maybe 17 kilometers per second.
So we are talking about nearly double the speed of a normal system asteroid.
And remember your high school physics. Kinetic energy is a function of the square of velocity.
Oh, right. E equals 1/2 mv squared.
Exactly. So doubling the speed doesn't just double the impact energy.
It quadruples it.
It quadruples it. This object isn't meandering, it is hurtling through the void. It brings an amount of sheer kinetic energy into our system that simply doesn't exist here naturally.
So today we are doing something a little different. We are not doing a movie review. We are taking a massive stack of real planetary science research to do a rigorous scientific deep dive into one of the most chaotic events possible.
We have data from University of Minnesota dissertations, Oxford academic papers on planetary formation, and advanced impact simulations.
The mission of today's deep dive is to answer the core questions. How much warning would we actually have? Could Earth survive the gravitational interaction alone? And if the absolute worst happens, what are the actual physics of a planetary collision?
It is a question that forces us to combine orbital mechanics, thermodynamics, and high-energy physics in ways that are, frankly, mind-bending.
We are going to look at the detection challenges, the gravitational chaos of the approach, and the terrifying thermodynamics of the collision itself.
Because the approach is a disaster in its own right, well before any physical rocks touch.
Let's start with the visual, though, because I found this absolutely haunting in the Reddit source material we pulled.
The backyard perspective.
Right. We established that this thing is dark,
Mm.
invisible. But eventually, as it gets close to the sun, the physics of light have to take over. What does this approach look like to a person just standing in their backyard?
Well, that depends entirely on the angle of approach, and this is where the warning time variable fluctuates wildly. If this rogue planet approaches Earth from the sunward side, it remains a phantom.
Wait, really? Even close up?
Think of a new moon. The side facing us is completely in shadow, and the object is lost in the overwhelming glare of the sun.
So it's hiding in plain sight, hiding in the daylight.
Exactly. In that specific orbital geometry, you wouldn't see it until the very last moments. You might see a strange distortion of the stars near the sun during a solar eclipse, but more likely, you would see nothing until it eclipses the sun itself or enters the upper atmosphere.
It would just be a sudden catastrophic darkness at noon.
Yes.
That is absolute nightmare fuel.
hmm
But let's flip it. What if it approaches from the anti-sunward side, coming from the dark of space opposite the sun?
That is the full moon scenario. As it gets closer to Earth, the sun's light finally hits the face of the rogue planet that is looking at us.
So it lights up.
Imagine walking out at night and seeing what looks like a full moon. Well, we know the moon is about 384,000 kilometers away. If an Earth-sized rogue planet were at that exact same distance, it would appear 4 times larger in the sky than our moon.
4 times larger. That completely dominates the night sky.
And it wouldn't be static. The moon moves slowly across the sky because Earth rotates. This object is moving because of its own immense hyperbolic velocity.
Because of that 29 kilometers per second speed.
Right. At that speed, it would cross the distance from the moon's orbit to Earth in just about 3.6 hours.
Pause right there. 3.6 hours.
That's it.
From the orbit of the moon to hitting the crust.
Yes. From the moment it passes the moon's orbit to the moment of physical impact, you would watch it move from east to west. Not just drifting, but swelling.
It would grow.
Visibly expanding minute by minute. Over the course of a single afternoon or evening, it would go from a bright, anomalous star to a moon-sized object to a horizon-spanning terror.
That puts the mission of this deep dive into incredible perspective. We want to understand the mechanics of that final 3.6-hour window, sure, but more importantly, the months leading up to it.
Because realistically, our telescopes would detect its gravitational perturbations before it hits the moon's orbit.
Exactly. So let's unpack the object itself first. We call them rogue planets, or sometimes nomad planets or free-floating planets. But I think there's a huge misconception that these are just asteroids that got really, really big.
Right, they aren't asteroids.
What exactly are we dealing with?
A rogue planet is formally defined as a celestial body of planetary mass, meaning it is big enough for its own gravity to pull it into a sphere, and big enough to have differentiated internal layers like a metallic core, a rocky mantle, maybe a crust.
The full-fledged world.
A full-fledged world that simply does not orbit a star. It wanders the galaxy completely alone. For a very long time, planetary scientists thought these were incredibly rare anomalies.
A freak accident of physics.
Exactly. But modern planetary science and recent survey data suggest they might actually be the silent majority of the galaxy.
I saw a number in the Newsweek research that blew my mind. Some estimates suggest these nomads might outnumber the stars in our galaxy by 100,000 to 1.
That is a very high-end estimate, often cited in more theoretical modeling papers, but it highlights the sheer scale of the unknown. Even the most conservative estimates suggest there are billions of them in the Milky Way alone.
Billions.
To understand why there are so many, we have to look at how solar systems actually form. We have this intrinsic bias of thinking of our solar system as this perfect, stable, eternal machine.
A clockwork mechanism.
But that is pure survivor bias. We think it's stable because we are here to observe it.
Because if it wasn't stable, we wouldn't have had 4 billion years for life to evolve and build telescopes.
Precisely. In the early days of formation, solar systems are incredibly violent, chaotic places. You have protoplanets smashing into each other. You have massive planetary migration, where gas giants like Jupiter move inward toward the sun and then outward again.
It's a gravitational mosh pit.
A mosh pit is the perfect analogy. And in a mosh pit, someone eventually gets shoved out of the circle entirely.
That is the gravitational scattering theory from the sources, right?
Yes. In this early chaos, you frequently get 3 body interactions, say a central star, a massive gas giant, and a smaller Earth-sized rocky planet.
They all pull on each other.
And when you have 3 massive bodies interacting closely, the orbital mass gets incredibly unstable very quickly. The lowest mass object almost always loses the energy exchange.
So the big planets bully the little planet.
They effectively steal momentum from the smaller ones or transfer their own excess orbital energy to them.
It's a slingshot.
It is the ultimate slingshot maneuver. The smaller planet gets accelerated so hard it reaches stellar escape velocity. It breaks its gravitational chains to the host star and flies off into interstellar space.
It didn't do anything wrong. It just lost the game of musical chairs.
It was in the wrong place at the wrong time during system formation.
So Earth is really just the lucky survivor that didn't get kicked out of the nest 4 billion years ago.
In a way, yes. We are the ones that managed to find a stable resonance. But there is another entire category of rogue planets we have to mention. Failed stars.
Round dwarfs.
Right. These are objects that form directly from collapsing clouds of interstellar gas and dust, exactly like stars do. They sit there in the middle of a nebula, gathering mass, getting heavier and heavier.
But they don't ignite.
They never quite get heavy enough for the core pressure to trigger sustained nuclear fusion. They don't turn on, so they just sit there, dark and cooling, drifting through the galaxy.
So we have billions of these things, ranging from the size of Pluto to gas giants larger than Jupiter, just invisible in the dark.
Yes.
If there are so many, why haven't we seen them? I mean, we have the James Webb Space Telescope, we have observatories looking everywhere.
Because space is incredibly dark, and these objects emit almost no visible light. They radiate a tiny bit of residual heat from their formation, mostly in very long infrared wavelengths.
But space is cold.
The background of space is about 3 Kelvin. Against that incredibly cold background, these dark, cooling worlds are effectively camouflaged. Our primary method for finding them isn't seeing them directly at all. It's a technique called gravitational microlensing.
This is the Einstein stuff. General relativity.
Yes, the magnifying glass effect. Light has mass, or rather, it follows the curvature of space-time caused by mass.
So gravity bends the light around it.
Exactly. So what astronomers do is we stare at a really dense field of distant stars, usually looking toward the galactic bulge in the center of the Milky Way, where the stars are packed tightly together. And we just wait.
What are we waiting for?
We are waiting for a dark, rogue planet to pass precisely between our telescope and one of those distant background stars.
And when it does, the rogue planet's gravity warps the light of that star.
It acts exactly like a lens. For a brief period, maybe a few days or weeks, that background star suddenly gets brighter.
Not because the star itself flared up.
No, the star is fine. It gets brighter because the rogue planet focused more of its ambient light directly toward our telescope, like a magnifying glass focusing sunlight.
But that requires absolutely perfect geometric alignment.
It does.
It feels like standing in a stadium in New York looking for a single gnat. And the only way you know the gnat is there is if it flies exactly in front of someone holding a lighter on the completely opposite side of the stadium.
That is a phenomenal analogy. And because that specific alignment is so mathematically rare, the fact that we have detected any rogue planets at all using this method suggests something profound.
It suggests there must be a massive, unimaginable population of them out there to create even those few chance alignments we've caught.
Precisely. If they were rare, we would never see microlensing events.
Okay, so we have firmly established the target, a massive, chemically dark, incredibly fast-moving object, a survivor of a chaotic birth now wandering the void.
The ultimate galactic nomad.
Now let's talk about the approach phase.
Yeah.
Because I think people immediately focus on the physical impact, the rock smashing. But reading through the University of Minnesota dissertation on what they call the geological orrery, I realized that just this thing entering our neighborhood causes massive, catastrophic problems.
This is the phase we call gravitational perturbation. Long before a physical collision, gravity reaches out and touches us.
Because gravity doesn't have a hard border.
Right, gravity is an infinite force. It gets weaker with the square of the distance, but mathematically it never reaches zero. If a rogue object, like say something the mass of a small star or a large gas giant, passes within 50 astronomical units of us.
50 AU. That's about the distance of the Kuiper Belt, right, where Pluto lives.
Yes, way out past Neptune. If it passes through there, it interacts with the major players in our system, and specifically it interacts with Jupiter.
And reading the orbital mechanics, you do not want to mess with Jupiter.
You really don't. Jupiter is the absolute gravitational anchor of our solar system. It contributes over 60% to what orbital dynamicists call the invariable plane of the system.
The invariable plane, what does that mean for a layperson?
Basically, it's the weighted average of all the orbits. Jupiter is so massive that it effectively stabilizes the orbits of everyone else, including Earth.
So if you move Jupiter even a tiny bit, you propagate that wobble to everything else.
Exactly. A rogue flyby tugs on Jupiter. Jupiter's orbit shifts slightly, and then Jupiter tugs on us.
And that trickle-down effect reaches Earth. But we aren't just talking about the calendar year getting a few minutes longer, are we? The research specifically mentioned changes to eccentricity.
Eccentricity is the mathematical measure of how circular or oval an orbit is. An eccentricity of 0 is a perfect circle. Earth's orbit is currently very nearly circular.
Which is great for us.
It's vital for life because it keeps our distance from the intense heat of the sun relatively constant throughout the year. But a gravitational tug from a passing rogue planet could stretch Earth's orbit. It becomes more elliptical.
And this connects directly to the Milankovitch cycles, right? The long-term climate cycles.
Exactly. Milankovitch cycles describe how very slight natural changes in Earth's axial tilt and orbital shape affect the global climate over tens of thousands of years. They cause ice ages.
But a rogue passage hits us fast.
Very fast. If our orbit becomes more oval quickly, we spend part of the year much closer to the sun, getting roasted, and part of the year much further away, freezing.
I saw the simulation data in the papers. It suggests that a passage just within the Kuiper belt, billions of miles away, could shift Earth's equilibrium temperature by up to 2 degrees Celsius solely through orbital mechanics. No physical contact.
Right, and 2 degrees doesn't sound like much to the average person checking the weather.
But in global climate terms, that is catastrophic.
2 degrees globally is the difference between our current climate and a global crisis of melting ice caps, rising sea levels, and the total collapse of global agriculture. The weather systems would become unrecognizable.
And that is just from a flyby that happens 4 billion miles away.
Yes.
If the object comes closer into the inner solar system, the papers say we enter the scattering regime.
Yes, the scattering regime.
Which sounds incredibly innocent, like scattering seeds in a garden. But in orbital mechanics, it sounds incredibly violent.
It is actually the most likely bad outcome. Statistically, space is mostly empty volume. A direct, head-on physical hit is like shooting a bullet and trying to hit another bullet in midair.
Extremely improbable.
But a gravitational boot is much more probable, because a planet's gravitational cross-section is millions of times larger than its physical cross-section.
So it just has to get relatively close to ruin our day.
Imagine an exo-Neptune, a rogue planet roughly the mass of our Neptune, passing between Mars and Jupiter. It acts like an immense gravitational slingshot. It could grab Earth with its gravity well and fling it into a completely different orbit.
Or worse, it could eject us entirely.
Yes. That is the ultimate nightmare scenario, known as planetary ejection. The rogue planet transfers enough of its massive kinetic energy to Earth that we actually achieve solar escape velocity.
Earth is ripped away from the sun.
The gravitational bond breaks. We would become a rogue planet ourselves, joining the billions of nomads in the dark.
That is a terrifying, profound concept. Earth drifting away from the warmth of the sun. The days would just get dimmer and dimmer. What does that timeline look like for us?
It's remarkably fast. Within a matter of weeks, the global surface temperature drops below freezing.
Everywhere.
Everywhere. The tropics, the equators, everywhere. Within months, the oceans freeze over completely, forming a crust of ice miles thick.
And the atmosphere, does it just blow away?
No, it doesn't blow away in an ejection scenario. It freezes. As the temperature drops toward absolute zero, the gases in our atmosphere would condense. First, the carbon dioxide would fall as dry ice snow.
Oh, wow.
Then the nitrogen and oxygen would literally liquefy, rain down onto the frozen oceans, and eventually freeze solid onto the surface. The surface becomes a total vacuum.
Is that it then? Is it just game over for the biosphere?
Oddly enough, astrobiology papers suggest not necessarily. Underneath that miles-thick crust of frozen ocean water near deep-sea geothermal vents, life could theoretically continue.
Because Earth has its own internal heat engine.
Exactly. From radioactive decay of isotopes in the core and mantle, it generates heat independent of the sun. So humanity, if we had the technology and warning, would have to become a deep-sea species.
You'd have to build cities huddled around volcanic vents like giant, highly engineered tube worms.
Living on a frozen, lightless spaceship drifting through the void.
A frozen spaceship Earth. That is a grim, grim survival. But let's move from the gravitational boot to the actual smash.
The physical collision.
Right. Say the astronomical odds are totally against us. A trajectory is locked in. We're looking at a direct physical collision. But before the rocky crusts actually touch, physics gets weird again.
Very weird.
We need to talk about the Roche limit. I feel like this is a term people hear in sci-fi movies all the time, but what does it actually mean physically?
The Roche limit is the critical distance at which a celestial body, held together only by its own self-gravity, will mathematically disintegrate because of the tidal forces of a larger body it is approaching.
It's the breaking point of gravity itself.
Exactly.
You said tidal forces, meaning the gravity pulling on the front of the planet is stronger than the gravity pulling on the back of the planet.
Precisely. Gravity weakens with the square of the distance. So if a rogue planet is significantly denser or more massive than Earth as it gets extremely close, it pulls on the side of Earth facing it much, much harder than the side facing away.
Because the near side is physically thousands of miles closer to the massive object.
Right. This creates an immense stretching force. It fights against Earth's own internal gravity that holds the rock together. If that external stretching force wins, the planet literally gets torn apart before any impact happens.
And we have actually seen this happen in our own solar system, haven't we? This isn't just chalkboard math.
We have. Comet Shoemaker-Levy 9. Back in 1992, it passed within Jupiter's Roche limit. Jupiter's gravity was so immense and the gravity gradient so steep that it ripped the solid comet into a string of fragments.
Like pearls on a string.
Yes, and then those fragments swung around and slammed into Jupiter's atmosphere sequentially in 1994.
So, if a super dense rogue planet, maybe a dead white dwarf star or a very heavy, stripped metallic core, approached Earth, we might not get hit by one giant ball. We might be spaghettified first.
Spaghettification is the extreme version of this physics, usually reserved for describing objects falling into black holes, but the underlying principle stands. Earth could be massively deformed, stretched into a prolate spheroid, like an egg shape.
The crust can't stretch like an egg, though. It's rigid rock.
Exactly. So the crust would fracture globally. You would have massive, continent-shattering earthquakes and unprecedented volcanism erupting everywhere simultaneously as the entire planet is kneaded like dew by gravity.
So even before the 3.6 hours are up, even before impact, the ground is literally tearing open beneath our feet and bleeding magma.
Depending on the density ratio of the two bodies, yes. But let's assume for the sake of this impact simulation that the bodies are roughly similar in density and remain intact until physical contact.
Okay, the rocks touch.
We are now looking at the physics of a giant impact. And I want to be crystal clear here. This is not like a meteor making a crater in Arizona. This is an entirely different regime of physics called hydrodynamic impact.
I was reading the Oxford academic paper on this. It's titled Exploring the Catastrophic Regime. And the terminology they use is so fascinating, but it sounds incredibly sterile for something so violent. They talk about thermodynamic processing.
Yes.
What actually happens the very nanosecond the two crusts touch?
It creates a state of matter we can barely simulate in a laboratory. We are talking about a head-on collision at tens of kilometers per second. The kinetic energy release is utterly beyond human comprehension.
What happens to the rock?
The moment of contact creates hypervelocity vaporized ejected plumes. The rock at the impact site doesn't just break into smaller rocks, it doesn't even just melt, it instantly flashes into superheated gas.
Vaporized rock.
And then a shock wave starts to travel.
A shockwave moving through the solid planet.
Yes. But this isn't like a seismic earthquake wave. It's not a P wave or an S wave. This is a high-pressure hydrodynamic shock front. It propagates rapidly through the Earth and simultaneously back into the impactor.
So it travels down through the crust.
Through the crust, through the silicate mantle, deep into the liquid outer core, through the solid iron inner core, until it hits the exact opposite side of the planet, the antipode.
The point on the globe furthest from the impact.
Yes, and this is the breakout moment.
And when this massive shockwave hits the other side of the planet, it doesn't just dissipate into the air, right?
No. It reflects. It bounces off the surface boundary of the planet and travels back inward toward the center as a release wave.
A release wave.
Also called a rarefaction wave. The initial shock wave compresses the planetary material to unimaginable pressures. The release wave follows behind it and rapidly decompresses that superheated material. And this is where the thermodynamics get truly wild.
This is the vapor dome concept I read about.
Exactly. When you shock silicate rock and iron core material to these extreme pressures and temperatures, and then suddenly release that pressure, the material enters a state of matter called a supercritical fluid.
Which isn't a liquid.
Right.
And isn't a gas.
It's a high entropy state where rock and iron behave like a dense, impossibly hot, pressurized fog. The impact simulation papers describe a vapor dome expanding outward from the planet's core.
You are saying the impact vaporizes the core of the Earth.
Yes. The study found a really interesting thermodynamic trend they called inside, outside, inside.
Huh.
Depending on the mass of the impactor and the collision velocity, the core particles deep inside the planet actually get trapped in these supercritical vapor states.
The inside of the Earth turns into fog.
The planet fundamentally stops behaving like a solid ball of rock floating in space and starts behaving like a fluid dynamic nightmare. It loses all structural integrity.
And this leads us to the phrase in the Oxford paper that absolutely stopped me in my tracks: catastrophic disintegration.
This is the absolute extreme domain of planetary science. Super catastrophic impacts. When the kinetic energy is high enough, the entire planet undergoes complete structural failure. The simulations show the deep core material expanding and forming what looks like a web.
A web? What do you mean a web? Like spider silk?
A macroscopic gravitational web-like structure. Because instead of remaining a cohesive sphere, the core and mantle are blown apart into dense, molten strings of material with vast, sparse voids of vapor in between them.
So it looks like a glowing sponge of magma.
It is a chaotic, rapidly expanding mess of hot rock vapor and molten iron strings. Now, the collective gravity of all that mass is desperately trying to pull it back together into a sphere.
But the thermal energy from the impact is pushing it all apart.
Exactly. It's a battle between gravity and thermodynamics. And in some specific mass regimes, say if the rogue planet is about 1/10 of an Earth mass up to 1 Earth mass, the colliding planets might temporarily form a toroidal shape.
Toroidal, you mean a donut. Earth becomes a donut of magma.
Briefly, yes. It forms a massive spinning ring structure. Planetary scientists call this a synestia.
The synestia.
It happens because of the immense pressure and the extreme rotational momentum imparted by an off-center impact. The combined planetary mass is spinning so incredibly fast and is so thermally expanded that it flattens out completely into a disk of vaporized rock.
How long does it stay a donut?
Depending on the cooling rate, it could be hundreds of years. Eventually, as it radiates heat into space and cools, gravity will win. It tries to coalesce the material back into a spherical planet. Or, if the energy was too high, it just disperses into a permanent debris field.
Yeah.
An asteroid belt where Earth used to be.
Okay, while the crust and core are turning into a web or a vapor donut, what happens to the atmosphere? The air we are literally breathing right now.
Gone.
Just gone.
Almost instantly. High-energy impacts are incredibly efficient at a process called atmospheric stripping.
I assume the shockwave handles that.
The initial shock wave and the subsequent thermal expansion accelerate the gas molecules in the atmosphere well beyond Earth's escape velocity. It basically blows the entire atmosphere off into deep space, like blowing out a candle.
I was reading in one of the space.com sources that there is actual geological evidence this has happened to Earth before.
There is very strong evidence, yes. When we look at the formation of our moon, the leading scientific consensus is the giant impact hypothesis, that a Mars-sized object, which we call Theia, hit the proto-Earth roughly 4.5 billion years ago.
But the evidence isn't just the moon itself, it's in the deep mantle rocks. We look at noble gases, specifically helium and neon isotopes.
Yes.
How do noble gases trapped in deep underground rock tell us anything about the air above?
It's about ratios. The specific isotopic ratios of helium and neon trapped deep inside the Earth's mantle suggest that the primordial Earth suffered massive catastrophic impacts that completely blew off its original early atmosphere.
So the air we have now isn't the original air.
The atmosphere we have today is considered a secondary atmosphere. It mostly degassed from the rocks much later through millions of years of volcanic eruptions.
So a rogue planet collision would essentially be a repeat of that violent infancy.
It would. It would cleanly strip away the air, instantly boil off the oceans into steam, and turn the crust and mantle into a global churning magma ocean.
It's a complete and utter reset of the planet.
It is a profound geological reset button. We would return to the Hadean eon.
Hadean coming from Hades, hell.
Exactly. It's the era of Earth's absolute infancy. A completely molten surface, absolutely no liquid water, extreme radiant heat, and constant meteoric bombardment. Any form of biological life is fundamentally impossible in that state.
Okay, that is the absolute worst-case scenario.
Yeah.
A head-on, total planetary demolition. But is there a scenario where it's just a flesh wound, say a glancing blow or a grazing impact?
Even a grazing impact at these velocities is utterly devastating. A grazing impact is actually what is theorized to create that synestia we talked about, that rotating vapor donut.
So even if it just clips us, it spins us out of control.
Even if the iron core of Earth largely stays intact, the sheer kinetic heat generated from the friction and the sheer force of the grazing impact would be more than enough to completely boil the oceans and thermally sterilize the surface of the globe.
And the debris.
Right, the millions of tons of molten rock thrown up into orbit would rain back down as liquid fire for thousands of years, keeping the surface completely molten.
So whether it's a direct head-on collision or a high-speed sideswipe, for humanity, the outcome is decisive.
Decisive is a very polite way to put it. It is an extinction-level event in the truest, most absolute sense of the phrase. It completely erases the biosphere.
Now, I can hear the listeners at home hyperventilating. We've painted a picture of unavoidable, terrifying doom. But we really need to contextualize this threat. Because while this is physically possible, meaning the laws of orbital mechanics allow it to happen, how likely is it really?
This is the most important part of the discussion. The probabilities are vanishingly small.
Give me the numbers.
The Newsweek article cited researchers who ran vast Monte Carlo simulations of the galaxy. They estimated the likelihood of a massive rogue planet even entering our solar system in the next 1,000 years is about 1 in a billion.
1 in a billion. Okay, that's genuinely comforting.
And the mathematical chance of that rogue planet actually making a close approach to Earth specifically, even lower. About 1 in 2 trillion.
1 in 2 trillion. But I have to ask, though, if we established earlier that there are billions, maybe trillions of these rogue planets wandering the galaxy, why are the odds of a collision so incredibly low?
It comes down to the incomprehensible vastness of the void. The overall density of physical matter in the Milky Way galaxy is incredibly, almost absurdly low.
Space is mostly space.
The distances between stars are enormous. You can have billions of massive rogue planets flying around in the dark, but the volumetric space they are flying through is so huge that they almost never actually hit anything.
It's this space is big defense.
Exactly. Imagine 2 tiny ants walking across the entire expanse of the Sahara Desert. Even if they are both walking randomly for years, the chance of them actually physically bumping into each other is basically 0.
So the solar system is just a tiny, tiny target in a very large desert.
Statistically, yes, we are incredibly safe. But the sheer existence of these rogue objects does raise a really fascinating philosophical point about our place in the universe.
How so?
We talk a lot about the fact that Earth exists in a Goldilocks zone.
Right. Not too hot, not too cold, just the right distance from the sun for liquid water.
But we also exist in a Goldilocks zone of gravitational stability.
We need the solar system to be boring.
We desperately need it to be boring. We need Jupiter to stay exactly where it is. We need all the planetary orbits to stay roughly circular.
The geological orrery concept from the U of MN paper shows us that the solar system has been remarkably, almost unnaturally stable for 4.5 billion years.
And that long-term stability is the sole reason complex multicellular life had the time to evolve. If we were in a slightly more chaotic part of the galaxy, or if our local planetary system was slightly more crowded, a gravitational perturbation would have sterilized the planet eons ago. We wouldn't be here to talk about it.
So a rogue planet represents the fundamental chaos that rules the rest of the galaxy, finally breaching our little sanctuary.
It changes how you look at the night sky. It's not just a static painting on the ceiling. It's a dynamic, moving traffic system.
A traffic system where most of the cars have their headlights completely turned off and there are absolutely no lanes.
That is exactly what it is.
So let's synthesize all of this for the listener. We started with this dark, silent approach, the massive detection challenge of fighting something with no light.
The ghost in the void.
Then we moved to the gravitational chaos, the planetary orrery getting smashed,
Yeah.
a flyby that messes with our orbit, changes our climate, or literally ejects us from the solar system before it even touches us.
A scattering regime.
And finally, the sheer physics of the physical collision. The Roche limit tearing the crust, the hydrodynamic shock waves, the vapor dome, the core turning into a supercritical fluid web. It is a terrifying but mathematically fascinating sequence of events.
It is the ultimate high-energy physics experiment. It clearly demonstrates that planets are not these permanent, invincible objects. They are actually fragile collections of silicate and iron held together by gravity, floating in a galactic shooting gallery.
But again, the physics are incredibly well understood, even if the event itself is highly unlikely to happen tomorrow.
Very unlikely.
I want to leave the listener with a final thought, something to chew on tonight when you look at the window. We often think of ourselves as the absolute masters of our domain. We build sprawling cities, we worry about the daily economy, we fight over imaginary borders.
We focus inward.
But if you zoom out just a little bit, we are just riding on a fragile rock that is drifting through a galaxy absolutely filled with ejected, violent worlds.
It brings up a really haunting question for me. If rogue planets are ejected during the chaotic formation of solar systems, if that scattering process is actually the cosmic norm,
And if there are billions of them out there,
are we simply the survivors who just haven't been kicked out yet?
that is the thought. Are we the lucky ones, or are we just next in line for the mosh pit? Next time you look at the moon, just imagine it 4 times bigger and rushing toward you.
Or better yet, don't imagine that at all.
Just enjoy the stability while we have it.
Indeed, long-term orbital stability is a profound luxury in this universe.
Thanks for diving deep into the science with us today. Keep looking up.
Just hope you see starlight and not darkness.